We will talk about elastic deformation. And what is elastic deformation? Well, I can illustrate that by bending on a band. Here I have an aluminum band. And I take this and put on a force. I just bend this band and we see that it bends out. It gives a deflection. So I deform it and then I take off the load and then the deflection goes back. What we see here is that the band goes back to its original shape and no deformation remains. That is actually elastic deformation. When you put on a load, make a deflection, take off the load, and the deflection goes back. And we have no remaining plastic deformation in the band. This can also be illustrated in different ways. We will now look at how it can be done in a diagram. Let's draw a diagram where we have on this axis the force and on this axis the deformation. The force can also be turned into a stress and we call it sigma. And the stress is the force divided by the unit area on the cross section. And the deformation can also be called the strain. We call it epsilon. So here we have the force or the stress, and here we have the deformation or the strain. Now we start putting on a force on a band. We increase the force and at the same time we also get some deformation. We continue to put on the force and we see that it actually is a linear relation. It goes to a certain point and here we start to release the force. We take away the force and then we follow the line back to zero. It means that as long as we go up and down along this line, we will put on a force and get the deformation, but the deformation will go back to zero when we release the force. This is the elastic part of the stress-strain diagram. We can also put a relation for this. We say sigma is equal to epsilon, and as it's a linear relation, it is a constant, which we call E. This constant, E, is called the elastic modulus, or the Young's modulus. And it represents the stiffness of the material. The E gives the material stiffness. It means that the slope of this line, which is equal to E, gives the slope of the line gives the stiffness of the material. This relation is called the Hooke's law, and it's valid, as we see, as long as this line is linear, and is valid only in the elastic part of the deformation of the material. We will now continue to discuss elastic deformation and elastic properties. We will start to compare some different materials. Then we will discuss what controls the elastic properties and elastic deformation. We will start to do some demonstrations to illustrate the coming discussions. We will start looking at the deformation of an aluminium band. We see a band here, and here we have a weight of 1 kilogram, which I put on the band. When I put on the load, we see that we get the deflection of the band. And as we have discussed before, if I take away the load, we see that the deflection goes back. It means that we are working in the elastic range. We make elastic deformation. Now we will compare this to a steel band. I put a steel band of the same thickness and the same length. Then I put on the same amount of load, that is 1 kilo, on the steel band. And what happens? Well, we clearly see that the deflection is smaller for the steel band. If we were measuring more carefully, we would see that it would be about 3 times smaller. It means that steel is 3 times stiffer than aluminium. The elastic module for steel is about 3 times as large as the elastic module for aluminium. If we want to compare to another material, we can take away the steel and put up a polymer, you can see that it actually bends down a little bit of its own weight. And if you put on the weight at the same time the weight, we see that it actually goes down in the bottom. It has a much smaller stiffness than the metals, and by this type of polymer. Now it would be interesting here to compare two types of aluminium. The aluminium band that is lying here is a pure aluminium band, and now we're going to compare it to a band which is alloyed and hardened. So we put the weight on the pure aluminium band, get the same deflection as before, and then we put the weight on the hardened and alloyed aluminium band. And now when we come to this stage, I used to ask my students, what do you think is going to happen? And of course you can also think about what do you think is going to happen now. Well, I put on this load, the same load on the same spot, and what do we see? Well, if you look very careful and measure, we see that the reflection is exactly the same for the two bands. It is the same reflection for the pure aluminium as it is for the alloyed and hardened aluminium. So, what conclusions can be made out of this? To summarize the results we just saw in the demonstration, we can say that the same materials have the same stiffnesses, independent of how material is treated or alloyed. But different materials, different base materials, have different stiffnesses. And why do we see that? Well, let's explain that now in the continuing discussion. And then we have to go into the atomic bindings. So let's do that. We start to look at a simple case with an ionic bonding between a chlorine atom and a sodium atom. The chlorine atom has 7 valence electrons and the sodium atom has only 1. It means that this electron easily is captured by the chlorine valence shell. So we get a chlorine atom or ion with 8 electrons in the valence shell. That means that we get an ion negatively charged, and the sodium will lose 1 electron, which means that the sodium atom will be a positively charged ion. So now we have 2 ions, 1 negatively charged and 1 positively charged, and they will be attracted to each other. It means they will approach each other and end up at a certain distance from each other. The question is, what is this distance? Well, if you look closer here into the inner shells, you have inner shells with electrons, which of course are negatively charged, and if you push the atoms close together, these inner shells will overlap, and that means that we'll have repulsion forces between these inner shells. So we have attractive forces between the ions, but we have repulsion forces between the inner shells, and these two forces will interact to give a certain atomic distance. If we look at this in a diagram, where we have the potential energy between the atoms on this axis, and we have the distance between the atoms on this axis. We see here that they have the attraction forces coming from the 2 differently charged atoms here, and we have repulsion forces from the inner shells here. So if we combine these 2 curves, we will have a curve looking like this, with an equilibrium point. And roughly we can say that this is the atomic distance. Anyway, we can say that this is atomic distance as the absolute zero temperature. We can see that if the atoms are pulled apart, we're going to move up the curve here. And then we take away the force that pulling them apart, we go back to this point. If they press them together, we go up on this side. If they take away the force that press them together, they go back to this equilibrium point. The curve we have looked at just now is called the potential energy curve, and that will be very handy to use when we want to discuss some certain material properties. We will start to discuss the elastic modulus, and we go back to the curve again. Yes, here we see the potential energy curve as before with the equilibrium point, that is the atomic distance, so the average atomic distance at this point. Atomic distance here and the energy here. If we derivate this curve, the energy curve, with respect to the distance, du dx, we will get a curve like this one down here, up here and goes down, like that. And if we derivate the energy, we'll get a force, but we can turn that into stress. So here we have the stress, and here we again have the atomic distance. But now we assume that we are pulling in the material. So it means that when we put a force onto the material, we will pull the atoms apart. It means that we will follow this curve. But if we make a tangent in this point, in 0 point, we'll have a straight line here. But that line can also be obtained by the second derivative of the potential energy curve in this point. But you see now that with this line, it's the same as the Hooke's law. Because here we have the stress, and here we have the strain. So when we start pulling the material, we will follow this line. Then we take away the load, and then we go back along this line, as we did before when we talked about the Hooke's law and elastic deformation. The interesting point here is that we can actually do the second derivative of the potential energy curve in this point and directly obtain the slope of this line. And the slope of the line, as we said before, it's the same as the elastic modulus of the material. So there is a direct coupling between the shape of this curve and the elastic properties of the material.